So, we have a question. You have a case where you have to set the determinant of this matrix equal to 0, right?
Mm-hmm.
Okay? And you get your characteristic equation that's equal to 0, right?
Mm-hmm.
So you have this is equal to 0. Well, this is the form a lambda squared plus b lambda plus c equals 0 with solutions. Lambda equals negative b plus or minus the square root of b squared minus 4ac over 2a. Quadratic formula, right?
Uh-huh.
With a equal to something, b equal to something, and c equal to something, right? So that's, and you solve that, and you factor the, turns out the discriminant factors, which you all figured out real quickly, okay? And that's just what we did in class, like 2 weeks ago Friday, okay?
Mm-hmm.
And I've seen many people do that, so does that answer your question? Because I recall you were one of the first ones to factor it. Okay?
We factored it in the inside. It becomes a factor and you can do the quadratic again, but I didn't know where to go from there.
Well, I think what you get when you do this is you get r plus lambda plus or minus the square root of,
You shouldn't have the lambda.
huh?
Where are you getting the lambda from in
Yeah,
your
aren't you
quadratic?
Sorry, r plus s. Again, that's middle circuit for you. Okay? And then you're going to get
I think it's r plus s minus 2 squared.
yeah, it's minus 2, and it's quantity squared. I'm just going to verify that. Okay? So very much like this, and you get then r plus s, and the square root of this is just r plus s minus 2. Right?
Mm-hmm.
And then that simplifies and gives you either r plus s or 1.
I get that.
Oh,
I get it.
Okay?
I don't have the word for it. That's not.
So you got to just follow the algebra through.
Is it r plus s or is it r plus s minus 1?
It'd be r plus s minus 1.
Yeah, it'd be r plus s minus 1. It has to be minus 1 because it's going to be between 0 and 1. I left that out. So I'm glad you all are on top of it. Very good.
So
Okay?
does that mean that one of the determinants will always be the same as one of the eigenvalues? Because
Yeah, 1 is always the eigenvalue. And of course, when we get the picture, we have lambda equals 1 here, right? Everywhere along this line, so any vector from the origin to any point on this line is an eigenvector with eigenvalue. Now, actually, no, this is not. Your lambda equals 1 is this one. Okay? Any vector along this line, of course, in the same dimension, you wouldn't have a vector going down here, but in other models you might. Okay? Any vector along this line is going to map to itself.
yeah.
Because it has to map along this line, and the factor, length factor, has to be 1, because that's what the eigenvalue tells you. Okay? And then along this line, lambda equals, well, it's r plus s minus 1, right? Okay? So any vector in this direction maps onto the same direction, but again, for a stochastic matrix, r and s both have to be between 0 and 1, okay? Which means r plus s minus 1 is going to be, for the same dimensioned model, generally, if you're using small percent transitions, r and s will both be more than a half. But they'll be less than 1, which means r plus s minus 1 is going to be a positive number, but it's going to be less than 1. Because r plus s is less than 2, that makes this less than 1, right?
Yeah. Will it
Okay.
be the same as the determinant because the determinant is r plus s minus 1 in this?
I don't know, work it out. Because that's a question, and that's a good, I'm not gonna say.
But so like if you get the same thing, do you have to prove that it'll always be the same, or if you get the same solutions, is that like?
Well, what do you get, what would you take the determinant of?
If you do like the, yeah, r minus lambda, s minus lambda.
The what now? This?
Yeah. If
No, you wouldn't do the determinant of this matrix.
R of 1 minus S.
Yeah, you'd leave the lambda off, because
Yeah.
why is the lambda there? You know, go back to what we're doing with the eigenvectors and eigenvalues, right?
Yeah.
So you would do the determinant of r, 1 minus s, 1 minus r, s. Okay?
Yeah.
Well, that's easy to do. Is that equal to this?
Yeah.
Well, if it is, then the eigenvalue is always equal to the determinant, right? Now, there are other arguments that show you why it ought to be so. Okay? Yeah?
I plugged that the lambda matrix into Wolfram Alpha to check myself, and
Uh-huh.
I plugged the lambda matrix